Okay, so CLISI 12. The first thing to notice, and I hope you might have noticed this, is that this vector field, you've already computed the divergence of that vector field. First of all, it looks a lot like the gravitational vector field for a point mass. So I don't know if you've noticed that. But you can look back into the section on Gauss's divergence theorem and note that the formula for the gravitational field of a point mass looks exactly like this. Just the constant k is written out with some actual constants. So having noticed that, I know that the divergence of this is 0 everywhere away from the origin. Now, of course, the vector field itself is undefined at the origin, so I have to steer clear of the origin. But other than that, surface independent. So the problem then is going to be to decide what new surface to pick. And it does get a little weird here. So here's what our surface looks like to begin with. We've got this sphere of radius 5 centered at 4 on the z-axis. So I think you can see that it intersects the xy plane in a circle of radius 3. A little algebra there, but so there's our surface. Okay, is everybody happy with that? Now, the vector field surface independent, so as long as I keep this boundary the same, then I can change the surface however I like. Uh-oh, wait, no, I have to be careful. Don't go anywhere near the origin. I'll put that in red because the function is not, the vector field is not defined there, and it's not surface independent. And you can't, so in other words, I can sort of move this surface however I like. I just can't sort of push it through the origin. So the first thing you're going to be thinking is, oh, well, the boundary is entirely contained within the xy plane. Let's just use the disk. Let's just use that disk. Problem, you're not allowed to. The vector field's not defined there. And so it doesn't work at all. So what you're going to want to do is strategize differently about what other surfaces would have the same boundary. Oh, by the way, let's see, this was outward orientation. So, let's see, outward, so, yeah, right. So it's oriented that way. So what other surfaces are, in some sense, convenient and also have the same boundary? And what I'm going to notice is that this vector field is radial, right? It points always straight away from the origin. So what I'm going to do is make a surface that has this as its boundary that kind of also has this sort of spherical kind of symmetry to it. And in particular, I'm going to choose this surface. That. And so instead of taking the ball and shrinking it all the way down into the plane, I'm just going to take it and kind of just shrink it down just a little bit until it gets down to, I'm just going to push it down to there and stop. Again, let's see, by the way, that had the outward orientation, so this also outward normal. So that was our original surface S. And now here's our new surface S2. Are we doing good?
If it's outward oriented,
yeah.
Like if the normal vector is pointing like directly down, it can't go through the origin, right?
Yeah, it's not allowed to go through the origin. Yeah, so
if it was pointing down, like on that flat surface, like wouldn't it be counterclockwise?
What's pointing down? I don't understand.
Like if the normal vector is just pointing down, like
you talking about over here? Like at a point like that?
Where the black orientation is, like if it was just pointing, like I think that space was pointing down.
I don't understand what's pointing down.
That's the normal vector. The orientation was like down.
Are we on S2?
Like down in the z-axis, like.
It's up on the z-axis though.
So, like.
I'm just not. You're talking about here?
Where? Oh, no, I think I'm just getting confused.
Okay. Okay. Let me know if you can reformulate your question. Just let me know. Yeah. Okay. So anyway, so I claim that S2 is going to be an interesting surface, and I know that the flux through S, because of the surface independence, so I claim that the divergence of F is equal to 0, and that means that it's surface independent, but not at the origin. So, but nevertheless, this is equal to the flux through S2. And I claim that this is going to be easy to calculate. For one thing, S2 has this lovely feature that it's a sphere centered at the origin. So I can write down its normal vector very easily. That normal vector, see, there's my vector field. The normal vector is going to be x divided by the radius of that sphere. And the radius of that sphere is 3. Let me pause for a second and make sure everyone's happy with that. Does everybody believe me that this is that unit normal vector there?
You said that was unit sphere, right?
No, this is a sphere of radius 3.
Okay, cool. All right.
It's 3 because you can make a little triangle. Draw this little triangle like this. And that red triangle, I know that height, this height is given as 4 because that center of the circle, the center of this top sphere is at 4. So that's 4. This is a radius of that top sphere, so that's 5. And by Pythagorean argument, that makes that 3. Exactly. Is everybody good? Okay. Okay, so there's our unit normal vector. What's our vector field? Well, our vector field it's the x vector divided by the length of x cubed. Okay, so x, and then divided by length of x cubed. So altogether then what I have is, well, I've got x dot x, that's length squared. Then I've got length of x cubed. And don't forget we've got a 3 over here in the denominator. This is now a scalar surface integral. And furthermore, length of x, I know over the entire S2. S2 is this sphere that is exactly the set of points whose distance away from the origin is 3. So these numbers here are always 3. So all together, excuse me, I forgot this k. There's a k in the formula for the vector field. Excuse me. Sorry about that. So there's k here. Altogether, I have k over 9. All of that is k over 9, which is a constant, which factors out. So I just get k over 9 times the scalar surface integral over S2 of ds. This is just the area of that hemisphere, and it becomes a geometry problem, and I'll let you guys wrap it up. Does that make sense? You asked me this question, I think. Isn't that right?
Yeah.
Does that make sense? Okay. Everybody happy? Now, this is a really interesting, but it's a hard problem, I acknowledge. What I love about this problem is that this is one of the few problems that I'm aware of where you have to choose a new surface that's not flat. Right? Most of the time we pick a flat surface because it's overwhelmingly the most convenient thing most of the time. Here, it was convenient to choose a not flat surface for that reason. Okay. All right. I'm going to stop the recording.